For this problem, we're looking at a simply supported beam. It's got a line load between A and B, which varies linearly with x, where x is measured to the right. Also a point load there at point C. And what we want to do is finding the internal shear force and the bending moment V and M for an arbitrary location at x somewhere between A and B. In order to get there, of course, we have to solve for our reactions first. So that's going to be our first step. So we're really looking at a problem or different aspects of problems involving equilibrium. So the first part here, again, is to find the reactions there at A and D. Well, the forces that are acting on the beam, we have a pin force there at A, so it's going to be AY. We're going to have a roller support there at D, so there's a reaction force of dy. We have the 200 Newton force acting there at C. And then between A and B again, we have a triangular load. And so that's going to be giving us some applied load P at a distance of D from the left-hand side. The load P is going to be the area under that curve, or the loading curve here. So it's 1/2 the base, which is 150 millimeters. And the height over there on the right side is 2 Newton per millimeter. So multiply that by 2. And again, because it's a triangle, I'm multiplying it by half there in front. So that gives 150 Newton equivalent load. The distance D, we know that that's 2/3 of the distance there between A and B, so that's 2/3 of 150. So in terms of where that point load is, D is at 100 millimeters from the left-hand side. Okay, so what I'm going to do first is make a moment equation, some moments, about point A. So I have the resultant force P. It's got a moment arm of D. It has a negative sign. I have the 200 Newton force. That 200 Newton force is going to have a moment arm of 200 itself, and that's going to be a negative sign. And then the reaction force at D, that's dy, that has a total moment arm of 250. It's a plus sign because that moment is in the positive k. For equilibrium, that sum is a 0. So from there, we see that the reaction force at the right side, the roller, is 220 newtons. We'll also sum forces in y. Summing forces in y, I get ay, I get dy, I have a minus 200, and then I have a minus p. For equilibrium, that is a 0. So from that equation, and using the value of dy above, I get that ay is equal to 130 newtons. So we've done the efforts that we need there to find the reactions at A and D. In order to find the internal shear force and the bending moment, I will make a cut at an arbitrary point, x, between A and B. So this mathematically, it says here that I'm looking at a beam which is of the entire length here, and mathematically I'm going to be making a cut that looks like that. Over on the left hand side, I have the same reaction force AY. I'll draw that in exactly the same way I did before. I'll put the shear force V. I'll put the bending moment M. And then what we have for this line load, this triangular load, which is acting over just the piece which I'm calling x, a length of x, I will just represent that by P, And again, it's going to be at some distance d from the left-hand side. So for this, I see that P, again, is going to be 1/2 the base, which is x, times the height there. Well, the height is going to be 2 over 150 x. Basically, I found the slope. The slope there, it's 2 Newton per millimeter over a distance of x. I'm sorry, over 150. That provides us with the slope. And then this multiplying by x gives that equation. So in terms of the triangle, this is the height and this is the base. Area is 1/2 the base times the height. So the P that I have is going to be a quadratic function. It's going to be x squared divided by 150. And we know the distance d is going to be 2/3 the distance across, which in this case is x. So with that, what I'm going to do is sum forces in y. Summing forces in y, I get ay, which I found before. I get minus p minus v. So therefore, from this, I see that the shear force at some position x is going to be ay minus p. And we found ay before, that was 130. And then I subtract away the p, which we saw was x squared over 150. I'm going to do a moment about point, looks like I'm calling that point E. E is where I made the cut. And when I sum my moments about E, keeping, of course, there the left-hand side, I have minus AYX. That's the reaction on the left-hand side. It's got a moment arm of X, and it's in the minus K. For P, the moment about E is going to be X minus the distance of D. And then I have the internal bending moment M, which is what I'm trying to find. For equilibrium, that is a 0. So from here, I see that the bending moment M is the reaction AY times X minus P times X minus D. And so what I get for the reaction, or I'm sorry, the internal bending moment, let me write that out, that M of X then is equal to 130 x minus x cubed over 450. Now, what we've seen up to this point is that we can find these things by equilibrium, as we've done here by drawing the FBD. But we also saw that from equilibrium we can check our work by comparing it with what the equilibrium results give. And that is that V of x, we know, is equal to dm dx. So if I take my expression there for m, I take a derivative with respect to x, I get 130, and I get x squared over 150. And the good news is that's what we got right up here. So this is just to make the point that we can get them by equilibrium, by directly using a free body diagram and writing down our equilibrium equations, and or we can look at the relationship that we also found from equilibrium in general. And the equilibrium relationship there is that V, the shear force, is equal to the derivative of the bending moment with respect to x. So again, our goal here was to find the internal shear force, V, and the bending moment, M. In order to get that, though, we first had to find our reactions. Once we had the reactions, we made the cut at the appropriate place, used equilibrium equations in order to find the shear force, V, the bending moment, M.